Those of you who aren't familiar or varying amount of familiarity with Java or with recursion in Java, recursion is really one of the most fundamental techniques that you will need to learn from this class as far as advancing your skills. Not only is it very powerful in algorithms, a lot of data structures are modeled and built this way as well. So if you get good at thinking this way, it certainly makes your life a lot easier as you go on in this discipline. So for recursion, I guess the first is kind of a cheesy example, but the answer to life's greatest mysteries are on the last slide. If you go to the last slide, you will find the answer to life's greatest mysteries. They're on the first slide, which if you go to the first slide, brings you back here. Now, this is a bad example of recursion in that it never ends. But recursion is literally where you, rather than solving the problem directly, you just redirect the problem. So the only way you're actually going to solve it is if every time you redirect, you've taken one step towards the answer, or you've broken the problem down to a smaller, easier subcase. As I mentioned, as you go on in this discipline, recursion is a technique that goes well beyond just the programming and into data structures, algorithms. I'm not even sure that there is an AI language that uses, I think they all, as far as I know last time, were using recursion to model AI. So if you take an upper level course and you want to learn how do we model intelligence in the computer, you're going to be heavily deep into recursion. Languages like Lisp and Prolog, you can probably download a free version of them and fool around with it now, but those don't have any loops. You can only use recursion to do repetition. This is the key thing to jog your memory about. Recursion has to have two steps. The first being a base step. This is the simplest case, the one which ends the recursion. And a recursive step, one that takes one step towards the answer or makes a smaller problem. So if you can't resolve what these two things are, there's no point in doing any Java code, because I mean, that part, basically, if you've done this before, you'll know that once you've solved those two steps, the rest of it's easy. The coding, in fact, looks really easy compared to some of the stuff we've done. So, for example, here's a simple Java method that would give you a countdown. And the base case in this is the typical 5, 4, 3, 2, 1 blast off type of countdown. So what ends the recursion would be the blast off command. And that will happen when the countdown is at 0. I would print blast off. So this is the base case. There can be no recursive call in this base case. It is supposed to terminate the recursion. So there's an answer here, and that answer is to print the blast off. Otherwise, what you do is you print the number we're working on and then count down one less. So if we wanted to do a quick hand trace, and again, this is a very useful skill if you're trying to think about how recursion actually works. If we do countdown 5, what it's going to do is it's going to first print 5, and then it's going to call countdown 4. So that's this step right here. Print the value and find the smaller problem, which is countdown 4. So this will print a 4 and call countdown 3. This will do a 3, countdown 2, and eventually we'll terminate at that base case. I guess in the future I'll have to start at a number lower than 5. But here's where I hit the base case. And blast off is printed. So what's actually happened in the computer, the reason I've drawn it this way for you to help visualize it, is that in the computer's memory, it's actually keeping all of that stuff in the memory in the computer's registers until it gets that final answer. And then what will happen is it returns to the last caller. So countdown 0 is finished. It'll return to countdown 1. Now it's finished. It returns here. And as I'm doing this, all that memory is collapsing and it's being freed back up to the system. But now the original call is over. and we got that print of 5, 4, 3, 2, 1 blast off. So this is what our goal will be to solve those kinds of problems. But you know, some are exceedingly complex for a loop and very elegant in their recursive form. So sometimes it's very easy for us to solve the problem recursively, which would be very challenging iteratively. But one fact you should know is that all recursion can be rewritten as a loop. Now, it may be that you have to do some tricks that you'll learn later with stacks and other data structures, but it's possible to do some form of a rewrite. I believe that's a mathematical proof somewhere. So here's the algorithm I'll just show you that really illustrates the power of recursion, or at least one that's, you know, hopefully simple enough that you'll get some sense of it. And so I'm just going to do some sort of crazy shape, and I'll connect it. And now I'm going to take this bucket and fill it. So what I'd like you to appreciate here is that paint will stop at all the edges when it hits those boundaries. So if I click, it doesn't go beyond the boundary. So think for a minute, how could you write a loop to do this when there's no regular pattern at the edges? Like, how do you know that when your loop gets to this section, that it is still part of the area which is not being drawn? Again, if you did a loop this way, here you paint, here you don't, here you paint, it's very complicated. I'm not sure that a loop exists that can take all this information in without, as I said, using the techniques of recursion and stacks and some other tricks to get around that. But that algorithm has a very simple Java code. Now, this is the simplest form of that algorithm. There are other forms which are more elegant and efficient. This one is just the simplest one I can show you. Now, it's very memory inefficient. It will probably crash a very small image if you don't try to optimize. But this is the idea. What's the base case when you flood fill? Well, the first thing you should think about is that if you've gone out of bounds with a pixel, then there's nothing to do because you're not within the image, you're outside of the image, so just return. So that's the first thing I've got here. And then the next thing is if the color that I'm currently at is the same as the one I'm trying to change it to. So in that example, if it's already red, there's nothing to do either because you don't color the red pixel red again, you're done. And then finally, if the color I'm looking at was not the one I originally clicked on, again, in that case, it was white that I originally clicked, then you're not allowed to change it because the boundary that you're filling would be all white. So this would return the simplest base case. Nothing to do, just abort. No recursive answer. Otherwise, what you will do is change the color to the one that you're headed to, and then ask each of the neighbors to update. So if you envision the if you envision a pixel, this is what you're doing is you're saying, right now, this is where we are, and I've finished the flood fill algorithm. Now it's your turn, your turn, your turn, and your turn. So I basically hand it off to the 4 neighbors and say, you do it. So eventually it will hit these diagonals, because now on the next call here, it'll say, you do it, you do it, you do it, you do it. But it's going to fill out, it's kind of like a breadth first, is growing like that to every pixel that's possible in this boundary. So that's what these recursive calls do on the neighbors. And then it just asks each of the neighbors, do you need your color changed? If you do, it will. And then it hands it off to the neighbors until there's no more neighbors to check. So that is a fairly complex example, not so much in the code, but in the problem-solving process. So what I'm going to do with you is try a few simple ones together. I'll lead the first couple, then I'm hoping you can help me with these. But the first one, if I want to do the sum of n numbers, this is what the sum of 5 numbers looks like. First of all, the base case is one that hopefully you're going to get the hang of quicker. So maybe you can tell me, if I gave you a detention and I said, You get to do the sum of n numbers. What would be the simplest case you would like to stay for? Oh, good. 1,000? A million? Simple enough, right? You just have to keep hitting the keys in the calculator. What would be the simplest thing to sum up numbers to? If this represents the sum of 5 numbers, how many numbers do you think would be the simplest to add up? Sorry? 2? Okay, that's definitely simpler than 5. However, I can still think of a simpler case. 1 is simple as well, and I can even think of a simpler case. 0, yeah, there's nothing to do at 0. I'm done. So the sum of 0 is my base case. Oh, thanks, but no thanks. Okay. And in that case, there's no sum. So really easy to answer that question. What's the simplest one? If n is 0, return 0. Otherwise, return... it's maybe not obvious if you haven't practiced with recursion, but the sum of 5 numbers, I could rewrite this as the sum of 4 numbers plus 5, meaning I'm using the same function against itself. Sum of 5 will become the sum of 4, a smaller problem, plus the 5 I started with. So what that would look like is the sum of 4 and then the number 5. So smaller problem, I'm going to have n plus the sum of 1 less. So let's just test it here. Let's try the sum of 10 numbers. So that is in fact correct, 55. You can verify that. The example one that we did together was the sum of 5 numbers. So that way you can see that it is 15 that's being produced. But notice again, there is no loop here. This is strictly asking the problem to be broken down smaller and recalculating itself. All right, another similar one is the factorial. This is one which starts with a product and it counts down. So 3 factorial is 3 times 2 times 1. Those of you who've taken some advanced math, this is how many ways can you rearrange 3 objects. So if there's 3 objects on my table and I want to shuffle them around, how many ways can I do that? 3 factorial is the answer. So the pattern continues. The only one that's a little strange at first is 0 factorial. And the way you can think of that is if I have nothing, how many ways can you arrange nothing? Technically, there's one way to arrange nothing, and that's that you get to do nothing with it. Because it's still valid if I give you 4 objects, it's still a valid arrangement if you do nothing with those 4 objects. So again, if you have nothing, there's still the same one arrangement where you don't do anything with it. So that is the base case here, the simplest factorial you can find. So I will say if n is 0, then you have to return 1. There's one arrangement. Otherwise, you get to return n times a factorial which is 1 less in size. So if you look at the pattern for 3 factorial is 3 times 2 factorial. And that's why I've written it this way for you. The pattern is also at 100. You'd have this massive product to do, which is simply 100 times 99 factorial. So that's the recursive case I've broken it down to here. So that one's on the slide. So let's have a look at what factorial 3 is. It still comes up as 6. So these are the ones we'll try to work out together. The first one is the Fibonacci numbers. So this is the Fibonacci sequence. If you've never heard of it, it's pretty famous. But basically you start with the numbers 1 and 1, and you add the previous 2 to get the next. So 1 and 1, the next number will be 1 plus 1, and that gives me 2. The next number is 1 plus 2, gives me 3. 2 plus 3 gives me 5, and so on. Okay, so base case, can anybody give me, if you had to think of the simplest Fibonacci number, or in this case, Fibonacci numbers, what could it be? All right, so any ideas? Where does the Fibonacci sequence start? At 1. So the first number is pretty simple. Okay. Is there any other simple numbers? Yeah, Fibonacci 2. So I'm going to call this, if it's a 1 or it's a 2, that's the case where you just, those are the beginnings of the Fibonacci. That's where we start and define it. And then the recursive step, I'll let you think about it for a minute. It says it's the sum of the previous 2. So that's the previous 1. That's the previous 2. So this will give you all of the Fibonacci numbers by that definition, which is recursive on itself. Okay, so Fibonacci number, why is it grumpy? Oh, it's got to be static, sorry. So the third Fibonacci number, let's pick a bigger one. 1, 2, 3, 4, 5, 6. We'll pick 7th Fibonacci number there. And verify that it does in fact come out to be 13. Yep. Okay, so again, very powerful in that once we understand the base case and the recursive step, the coding is really simple. So here's the one that's a bit more challenging. It's Euclid's algorithm for greatest common factor. Perhaps you've written this as a loop before, but this is the algorithm itself. What you do is you take the larger of the two and divide it by the smaller. If the remainder is 0, you know that the smaller is already a factor. That has to be the greatest common factor. Otherwise, we take the greatest common factor for the smaller and the remainder. So let's try this with 60 and 105. I'll do this with you just so you can see a hand trace. Those of you who aren't fans of hand tracing, you're going to need to get a little more used to hand tracing because it's very powerful in helping you understand the problem. So if I did this, I would get 1 with remainder 45. So now I repeat the problem with the smaller and the remainder. So this will happen once with remainder 15. And again, it's not a 0 remainder, so repeat it. 45 divided by 15. Repeat with the smaller and the remainder. This is going to give me 3, remainder 0. So according to Euclid, 15 is the GCF of 105 and 60. Now that's pretty powerful because if you think about other alternatives, it would be like, okay, let's try 104, 103, 102, 101, 100. You know, some other strategy might be better, count by 5s, count by 10s, but this will work for any two numbers, any two integers anyway. So if I want to implement that with you, let's try it recursively again just to appreciate what the code looks like. So I've got public static int GCF, and I'm going to specify here that this has to be the larger and this has to be the smaller. You can do your own check in the code and then make sure you're doing it, but let's assume that the person reads my documentation and uses the correct larger smaller on their own. Once I've set it up, I don't need to check it anymore. That's why. So here in this case, I need to know the remainder before I can make any decisions. All right, the base case is if the remainder is 0, return the smaller. This is the simplest thing that can happen with greatest common factors. For example, if I wanted to know what's the greatest common factor of 200 and 100, done, it's 100, because immediately it is a factor. Okay? Otherwise, what I have to do is return the greatest common factor of the smaller and the remainder. So compare that to the loop that you would need to write. It's not that the loop is overly challenging, but again, I think you'll appreciate the simplicity there. So let's go and verify what's the greatest common factor of 105 and 60. 15, just like our hand trace. Pascal's triangle, if you've never played with it, it's very similar to, like, it's kind of like Fibonacci numbers. What you do is you take the two above. So 1 plus 1 gives me a 2. 3 plus 3 gives me a 6. 1 plus 3 gives me the 4. And so on. You can build this up for as big as you want it to be. Now, this also works as a recursive problem because the number you're looking at is the sum of the two above you. So what I would invite you to do, and I won't do it here, is this would be a really good challenge for you. Can you do Pascal's triangle recursively? So I'd invite you to try this after your exercises. Think about what the base cases are. Maybe you can tell me that, because remember, the base case should be not exactly obvious, but it should be easier to find. So what do you think? You can explain it visually to me, but there's something pretty striking about Pascal's triangle. You look at it, what do you notice? All of the edges have ones on them. That is the base case to check. Am I on the edge? Am I the first thing on the left side or the last thing on the right side? Then I know it's just a 1. That's the simplest way of answering Pascal's triangle. Geez, I don't know why this keeps coming up, but anyway. And then you'd have to think about the recursive case I explained to you, the one above, or sorry, the 2 above, the one you're on. So here's one thing that you have to be aware of. If we have a choice, we will always pick iteration. Plain and simple. It is faster and more efficient to execute your code with a loop. And in fact, some compilers will do this for you. If they recognize tail recursion, so let me show you the difference between tail recursion and non-tail recursion. Tail recursion is the last thing in your code is recursive. This is like the bottom of your loop. It basically would tell Java, this is the code to execute inside the loop, and this is where your code now goes right back up and does it again. Recursive case, again. See, it's actually going to make kind of a, closer to a loop than it would before. Although there is a recursive call here at the end, this is not tail recursive because there's still more things to do before your last statement. So for very basic cases, this is tail recursion as well. The last thing in your code re-ups the recursion there or makes a loop. Some compilers recognize that and behind the scenes will translate it for you. But this is the program trace for Factorial. I'm going to do Fibonacci with you just so you can see what it really looks like. So let's go back here, and I'll call this public static int fib loop. And I've got two terms. Actually, let's do a sum. So the first thing I can do is I can say, let's see here. Yeah, I'll go with this. Okay, so So while the term is less than that Fibonacci number I'm after, my term goes up 1 each time. And I have to take the previous 2 and add them together. So I'll call this term 1 is a 1. Term 2 is a 1. And I'm going to use the next term here. So next is equal to term 1 plus term 2. Term 1 is going to become term 2, and we'll advance them forward. So let's see here. Actually, I won't need a temp for that. So term 2, so term 1 equals term 2 now, and term 2 is the next one in the sequence. So it'll go all the way through until I return next, and Java's grumpy because I should initialize this. So that's fine. And I guess for I should start this at 1, because if my loop doesn't run at all, then let's see, it won't. It'll stop before I return a 1. Actually, I think it'll be more readable if I go like this. Term 2. And I start, now I'm on term 3. And that's how many times I would need to do it there. All right. So what I'll do is I'll just give you a comparison of what these run times look like. Let's try the Fibonacci number of the 20th Fibonacci number. Now it'll actually tell me the run time at the end of this. So you said it took 2 seconds. Now we'll go down to the looping case. And they don't match, so I do have to work out a quick bug here. Okay, so the term here should have been 2. So let's try something bigger where the significance will build up. If we try the 100th Fibonacci number with a loop, well, the integers have overflowed. It's gone out of bounds, but it still took the same 2 seconds. Meaning it's not really discernible from the case where it takes to do 20. This one, however, because of all the recursive calls that need to be resolved, is going to run for a while. So we'll come back. I'm not sure how long this is going to take, but you can already see it's still going. And I'm not sure if it'll even finish for us. But we'll have a look later. So one thing I'm going to ask you to do is a fractal. And where you're going to need to load your code from is I've got a little simple graphics library for you to download. And the way you import it is you go into your project. And under this libraries folder, you right click on it and say add a jar. And you pick up the JGraphics one. So this will just allow you to do some of the basic graphics stuff, so that you can draw a fractal. And to import this package, this will import all the drawing features for you. All right, so let's see if it's even ended yet. Nope, still running. So what I'm going to try to do with you, and I'm not sure if we'll have time to finish it, but is the H fractal. So fractals are naturally suited to recursion. If you have a look at some of the ones that are available on just Google Images. This is the H fractal. Here's a bigger picture of it, so we might as well have a look at that. But it's going to make a very crafty picture for us. And let me introduce you to it. This is the H fractal. That's all it is, and that's all I'm going to code. However, if you want to get the next H fractal, it goes like this. Okay? And you can keep going to produce this pattern, but all they are is, again, more H fractals. So if you think about the base case of drawing that versus drawing the entire thing at once, it would be quite a challenge to use nothing but loops to draw this. So there's a whole host of fractals you can choose, but I'm going to do this one with you. Okay. So I need a few parameters to keep track. Oops. So just so you can see what I'm coding it from, this is the window you want me to draw the fractal on. The midpoint is this one here. In the next one, this is the midpoint. The next one, this is the midpoint. So that's where you start the H fractal from and what level you're on. So basically what will happen is eventually I'll get down to level 0 where I don't need to do this anymore. So that's my base case. There's no more H fractal to draw. Otherwise, what I need to do is figure out how do I draw this from this midpoint. So I'm going to give you these coordinates here. So midpoint's X. And sorry, I did miss one in here. I need to know how big you'd like for me to draw it. So go half the size to the left. And it's going to be very similar here, so but this time I'll do top right. The only difference is now I'm going to the right, so I will add that coordinate to the middle. You'll need the bottom left. And this time I'll be backing up in both, left and down, and bottom right. So I'll be going positive here and negative here. And the midpoint left and the midpoint right. All right, so I will just show you the points on that picture. These are the ones that I'm calculating. Top left, top right, bottom left, bottom right, and this is the left side and this is the right side. So what I'm going to need to do now is draw some lines. And I'm just going to connect the points. The right, okay, so now all that's left to do is draw it before we make the recursive call. So I'll draw those lines that I just calculated. So draw the right and draw the midline. And then finally, make a recursive call here to the next level. So H fractal, use the same window. This is the new midpoint for one of them, the top left. Half the size or it won't fit, and one level less. So I have to do this for the 4 H's that I'm going to draw. So the top right, the bottom left, and the bottom right. So I'll just see if we can quickly run it here. And oops, sorry, I haven't actually put it into main. But at this point, I'll have an H fractal. So let's do all right, so this should pop up. Thank you for your patience there. I will make this available so you can see it online. But I believe our original run is still going with the Fibonacci numbers too. It's being so inefficient. Okay. All right, anyways, I realize you guys need to get moving, but we'll have to come back to this one later, okay? So thank you, and we'll talk to you again tomorrow. Alright, so that was why they came up crisscrossed. Should have been bottom left there. Alright, and there's the final result.